Okay. So let's see. Your TAs and readers worked very hard to get the midterm graded, and so the results are already posted. And I think you probably felt it. So by and large, people did much better on this midterm than the first midterm. So that was really good. So the mean was 57. Remember, this time it's out of 100. So it's the last midterm was out of 120. Standard deviation is approximately 20. There were a lot of people who got close to full points. Nobody actually got 100, but I don't know if it matters so much. There was a very big spread, and it was it was really more or less a bell curve, but with so it was a very nice spread. I don't know how people felt about the midterm. Is that roughly your? Were people pretty happy with it, or did you have no? Please, actually, do tell me. Yes. Yeah, good. Anyone want to give feedback on how you felt? So I would love to hear what your experience of the midterm was. Does anyone want to say how they felt? Yeah. There wasn't time. Oh, good. Okay. All right. Yeah, no time pressure. Did people agree mostly that there wasn't time pressure? Okay. Okay. Great. And any other feedback? Any other comments on how it felt? Yes. The last question was really hard. Okay. Maybe I'll address that right now, and just very very briefly, right? Okay. And yeah. Yes.
I know a lot of people were confused. I believe it was 1C regarding 1,000 steps being 1,000 lines or 1,000 basic instructions. So a lot of people thought it meant 1,000 lines. Thought the stuff was in those first 1,000 lines.
Mm-hmm.
So it was a question on accountability.
Yeah. So I think we I don't know where you were sitting, but it was clarified in the course of the exam, right? There was either something put up or an announcement about it. Okay.
I don't think I didn't see the announcement that clarified it. I don't know if that was just me being focused or if it.
Yeah, I don't know. I think it was announced in every class because it was coordinated. Yeah? Any other comments? Yeah. Like number 3, which was the false diagonalization. Oh yeah, good. Yeah. I'm sorry. Yeah.
I feel like there's a good amount of space everywhere except for 5C.
On 5C you ran out of space to write your answer, you mean? Yeah. Oh, I see. But could you just write it somewhere else and point to it? Okay. Yeah. So I guess we do have to make sure that. Okay. So good feedback. Yeah. Okay. So yes. Hey.
Positive feedback. I like that you tested pretty much everything you covered. There was a balance of everything that we covered.
Okay. Good. Okay. So the comment was it seemed to test a good balance, meaning it tested pretty much everything that was covered. Yeah. Oh yeah. So question about the extra credit, how we'll factor that in. So as you'll notice, if you look at the release grades, they're out of 100. In fact, so far the extra credit hasn't been graded, so it'll be graded maybe today or tomorrow. And then I'm sorry. Oh, it has already been graded. Okay. Oh, it has. Okay. So sorry, I'm not up with the time. So the extra credit has been graded. It's completely separate from the rest of the exam, and it'll be handled completely separately from the rest of the exam in the sense that you'll have your points and they'll count separately, and then this will be a separate thing when we are assigning grades, maybe just to if you're close to a borderline or so it's the way we treat extra credits also on homeworks. It's much more, it's separate from all your other grades. Okay. Okay. So yeah. Okay, so this is a question that's come up often. What happens if your midterm 2 grade is much better than midterm 1? Basically, at the end of the semester, I'll look at trend lines. If you started off not doing well, but then you eventually started doing well, then that'll count for something, but it'll be entirely subjective, right? So there isn't a formula for that, but I will try to take it into account. Yeah? Okay. Let me just say a little bit about, let me go over one of the questions and then question 4, and then I'll try to go over a little bit about question 5 just to clarify what we were trying to do there and why we thought it was relevant. And okay. So question 4, by the way, the thought in making up that question was, the idea was to both test, but also, the thought was that maybe by the end of the midterm, some of you would understand error correction better than you did when you went into the midterm. Okay, so that was the hope. I don't know if it actually worked for anybody, but the thought was, we were going to go back to the very basics of error correction and sort of try to see, could you look past the formulas and go back to where we started the explanation from. And where the start of the explanation came from was we said, okay, so imagine that what you're trying to do is these are the 2 points, these are the 2 messages that you have. So it's maybe this is 2 and that's 3. So that's your message. And now what we do is we take a straight line through that, and now we transmit a number of points. So maybe the transmitted points were this, this, and this. Okay? And now the first part A said, so for A, I think, said, well, suppose that you had 2 errors. Now, remember, when you have 2 errors, you have 2 transmitted points, you are supposed to send 6 points, right? N plus 2k. If you have two errors, you're supposed to have twice as much redundancy. We don't have twice as much redundancy. So now what goes wrong here? So now your received points, these are the transmitted points. The received points are, let's say, this, and that. Okay? And now what you want to do is reconstruct the polynomial. So how do you reconstruct the polynomial? Well, you say, look, there's a line going through, if I look at the original line, it goes through 3 of these points. Is it possible that there's any other line that goes through 3 of the received points? So among these x's, could there be any other line that goes through 3 of them? And so the question 4a said, suppose you're told that this point lies here, where would you place this 4th point so that the recipient gets confused, so that there's not just this line but some other line as well? And so now you had a choice, right? You could make up another line by just saying, well, I want a line to go through this, and, well, that one there, right? Or you could make it up so that it goes through this, and something here, maybe like that, right? Or you could make it up so that it goes through this, Okay, did we already do that? Well, okay. Yeah, okay. But you see the point. You take this one that was an error. You take one of the correct points, and then you can join them with a line, and you can say, well, I'm going to place the third point here. And if it was here, then here's another line that goes through, right? So if this is what this error was, then there's another line. And now, how does the recipient know which one it is? It could be this one, or it could be this one. You don't know. Okay, so the recipient gets confused here, and that's what was being tested there. Now in 4b said, well, now suppose you do the right thing. The right thing you're supposed to do is these were you sent 6 points, and now you have 2 errors. Okay, so what it said was, show that if you have 2 errors, there's no way that the recipient can get confused. Now, of course, this is what your formula tells you. N plus 2k is sufficient. We proved it in class. But it said, prove it just in this case, just to show that, just to see that you actually understand what's going on. Okay, so what happens when you have 2 errors? So you have 2 errors. There's something here, and it doesn't matter where these points are, right? So you want to so if these are the received points, you still have a line now that goes through 4 points. And now you want to say there's no other line that goes through 4 points. This is the only one. So now the recipient, if they figure out which line goes through 4 points, they know this is the only one. That they've reconstructed this one. Okay, so you want to say there's no other line that goes through more than 3 points. And how would you show this? Well, you would say, look, we know that a line is determined by 2 points. So if you use more than one of these 4 points, then you know that this is the line that goes through it, right? So as soon as you pick 2 of these, so if you pick this one and this one, okay, it doesn't matter what else you pick. There's only this line that goes through these 2, right? So therefore, you can pick at most one of them. So if you pick one of these, what else can you pick? Well, you can pick the 2 points where you have errors. But that still gives you 3. Right? So no other line can go through more than 3 points. That's all you had to say. Right? That's what we were looking for. Right? Does this make sense? So is it clear why what was the thinking behind the question? The thinking was, look, this is really what error correction is all about. Of course, it gets more complicated when we talk about higher degree polynomials, but the way we started the story about error correcting codes was by talking about lines, right? Because it's the simplest case. Because once you understand why it works, then we can generalize it and we get more complicated formulas. But nothing changes conceptually. This is really what error correction is about, right? So okay, and that's what this question was. Well, it was meant to be both a test, but also a reinforcement, so that by the time you were done working through this, you really understood error correction better than when you went into the test. So hopefully it worked for some of you, and hopefully it works for even more of you when you work through the question later. Right? Okay, so let me just do a couple of minutes on question 5, since somebody asked about it. So on question 5, what was the whole point there? So the point was, we wanted to say, I don't remember how the question actually went, but let's pick one, something like this. So suppose you're doing RSA mod n. Okay, so you're working mod n, and now. Suppose that you pick, so you have your encryption function, which is x to the e mod n. Okay, but now, suppose that you pick r at random. Suppose you pick r to be uniformly random in 0, 1 through n minus 1. So it's a completely random number. It has probability 1 over n of being each one of these. the question was, show that E of R is also random. Is that what it said, or was it the other way around? If E of R is random, then R is random. I don't remember which one. It was this one. Okay, so it was this one. If R is random, show that E of R is random. Now, what does it mean? E of R is random. It means that probability. Oh, right. Yeah. Okay. Show that E of R is uniform. Okay. So that's what we want to show. So we want to show, probability C equal to E of R is exactly 1 over n. But now, in what way can you get C? What must R be in order that E of R equal to C? There's only one value of R because RSA is a bijection, right? So once you encrypt, the probability you get C, there's only one way you can get C, which is if you pick R, pick this particular R, right? And what's the probability you pick this particular R? It's exactly one of these values between 0 and n minus 1. So its probability is 1 over n. That's what we're given. And so that's what it was saying. So it was just sort of reiterating the fact that you knew that RSA is a bijection. So if you pick a random number and so what's it doing? It takes 0, 1, 2 through n minus 1. And it just maps these in some way, right? So in such a way that everything here gets mapped to a unique thing here, right? So now if you're picking all of these equally likely, what happens after you map here? You get each of these with probability 1 over n, right? And that's all it was asking you, right? Now, if you worked your way through to the first 3 parts were basically trying to help you solve the extra credit, which was initially part of the exam, and then we realized it might be too much, and so we made it extra credit, and because it might have been too long and too hard, and so the first 3 parts were just these basic properties of RSA and probability put together to help you work through to the final part, which is actually something interesting, which is something that's interesting from the point of view of cryptography or security, right? And so, but the main point here was just understanding that RSA has a certain structure to it. Okay. Is that clear? Any questions about either of these? Or yeah. What about part B? Part B just said, encryption of AB equal to encryption of A times encryption of B. And that's just because A to the E, B to the E, mod n, is AB to the E when you're working mod n, right? So it's okay. So okay. What's the point of this? The point is, the way you want to think about encryption is that what it does is it completely scrambles the value, right? That's what RSA is supposed to do. Now, if you completely scramble the value, there should be no structure left. But in fact, RSA has structure to it. It's because we are raising to the power of E, and that has the property that when you multiply two numbers, then raise to the power of E, it's the same thing as raising to the power of E before you multiply. And so that's something that you know about RSA messages. That's not that you would not expect if you were just saying it completely scrambles up all the bits in some way, right? So so it's important to discover in what ways your crypto system, like RSA, is not really random. It actually has structure to it, and whenever it has structure, you can exploit it in some way. And so that's what the extra credit part of the question was. It was saying, here's a way that you can exploit the structure of RSA. So you have to be careful about certain things with RSA. Yeah? Okay. Yeah. Part C. What was part C? Oh, it was. Okay. Yeah, sorry, I have it here. It's something about multiplying, right? You were supposed to show that if GCD of A and N equal to 1, then encryption of A times encryption of R is random. If R is random, right? Okay. So you could do it in one of two ways. I guess you could just say, well, encryption of A times encryption of R is the same as encryption of A times R. Right? You already know that from part B. But now, if A is relatively prime to N and you take A times R, I claim that that's also random. If R is random, then A times R is random. Right? Why is that? Because A has a multiplicative inverse. So multiplication by A is a bijection. Right? So you have the numbers 0, 1, 2, so on up to n minus 1, 0, 1, 2, up to n minus 1. When you multiply by A, what happens? Well, you cannot get a collision, right? You cannot have two things that when you multiply by A, they give you the same thing because A has a multiplicative inverse. If this times A equal to that, right? Then if you know something times A equal to this, then that something is uniquely defined. You just multiply by A inverse and you get back what this is. You can't have two different possibilities. So it's got to be a bijection. But then once it's a bijection, you've picked this at random, you're also picking that at random. Right? So if R is random, implies A times R is random. Mod n. Everything is mod n. I'm not writing it out. A times R is random. Why? Because times A is a bijection. Okay, but now A times R is random. What's E of A times R? Well, we already said from part A that if you take a random number and you apply the encryption to it, it's a random number. So that's it. Right? That was one way you could do it. You could also do it. There were many ways of doing it. There were 2 or 3 different ways of doing it, but they all boil down to just saying the same thing. Multiplying by A is a bijection, so it doesn't change the fact that you've picked a random number. Right? Yes.
You similarly explain the same logic to describe without mentioning bijection at all, where we refer to parsing and how A and R become relatively finely fused, but we've already quickly showed that you'll still get the probability of 1 over n. Is still going to receive any credit for that?
I'm sorry, I didn't completely follow, but
Explain the same logic without explicitly stating bijection. We still do not receive credit for that?
I don't know what exactly you did, but my guess is if you did anything reasonable at all, you got credit for it. Yeah? So, okay, but we can take that offline and look at the actual. Yeah? Okay. Any more questions? Okay. Yes.
Regarding practice midterms, I think it would have been nice to have some solutions ahead of exams so we could get some quick feedback.
Actually, no. That's a very good point, and I think I heard that from somebody else as well, and I think we'll try to do that for the next exam. I was actually also thinking if at all possible, we'll try to give you some, We're trying to sort of put this together, see if we can do this. Just trying to understand from here. Well, what did people need to understand in order to get a B in the class, etc. Right? So to the extent that we can say that for the final, we'll try to say that. Here are the skills you need to master in order to. Right? Here's what you need to master if you really want to prove that you got an A, etc. Right? So you have some sense of what you're heading for. So we'll try to do that if we can. It's not necessarily that easy to just pinpoint, but okay. Yeah. Anything else? Okay, so shall we move back to probability? So today, today I'm going to talk about two applications of probability to hashing and load balancing. Okay. Now, hashing and load balancing, these are very basic operations in computer science. Right? They come up all over the place. And it turns out that to analyze these, there are certain basic things you need to analyze about these. And what we're going to do today is we're going to study a very simple model, very simple probabilistic model. It'll look like nothing at all. And then we'll see how to apply it in these two contexts. Okay, so what's this simple model? It's something that we've already seen at some point, which is balls in boxes, balls in bins. So we have n bins. Okay, so we have n bins. We have k balls. And so they're numbered 1, 2 through k. And now we place these balls in the bins at random. Okay? So what does it mean? So you place ball 1 uniformly at random in any of these bins, and then you take ball 2, place it uniformly at random, and so on. And now there are two questions this is the sort of question we'll be interested in. How large should k be such that? So what's the largest k such that probability that you have two balls in some bin greater than or equal to two balls in some bin is still less than or equal to half. Okay? So let's this is a mouthful, so let's try to understand. We are putting, we have k balls, n bins, k is smaller than n. Okay? Because as soon as k is larger than n, at least one of the bins is going to contain more than one ball. But now imagine that k is much smaller than n, right? Now, what we'd expect is, if k is very small, we'd expect that no bin will actually contain two balls. So now we want to make k as large as possible so that most of the time we don't see two balls in one bin. Okay? So we want k as large as possible such that most of the time every bin has either 0 balls or 1. Okay? So that's question number 1. Question number 2 says, suppose now that k equal to n. Okay? Just for example, we could choose some value of n, like n, 2n, n squared, whatever it is. Now we want to know how large. What's the maximum occupancy that we should expect, right? So most of the time, do we expect to see? So if k equal to n, if you throw n balls in n bins, okay. Now, and we want to look at that bin which has the most number of balls. Can we say something about how many there would be in that bin? Okay, most of the time. Let's say with probability more than a half. What can we say about the maximum occupancy? Okay, so what we'll show is that the answer here is, so the answer to question 1 is square root n. Okay? As long as you're throwing square root of n balls into n bins, we'll show that, in fact, the chance that 2 of these end up in the same bin is less than a half. Okay? And the answer here will end up being roughly log n. Okay, so if you want it to be more precise, then it's roughly log to the base e of n divided by log n. And if you want it to be more precise, then you have to look up the notes. Okay, so this is known in great precision, and we'll show something like this today. Okay? Okay. So now let's go back and understand, why are these numbers important? Why do we want to understand these kinds of numbers, and what do they help us understand? So the first thing to understand about this is very simple model, right? You're just throwing balls in bins. You're trying to understand something about how the balls are distributed in the bins, and somehow that has something to do with hash functions and with load balancing. So we have to see why that is the case. Okay, so before we get started on that, what's the probability space we are working with? What's the sample space? How big is the sample space? Yeah. It is n to the k. Right, because what's a sample point? A sample point is you place each ball in some bin. Right? There are n ways to place the first ball. No matter where you place that, there's no restriction on the second ball. It can go anywhere. Right? So there are n ways of placing the second ball. No restrictions on the third one. So it's n times n times n times n, k times, so it's n to the k. Okay? So what's a hash function? Or hashing. Okay, so this is a data structure for storing a set. Okay. So you're trying to store a set S, and you want to answer queries such as, given a new element X, is X an element of the set that you've stored? Okay. If it's not an element of the set X, maybe you want to put it into S, so you want to update S so that S includes X. Right? So those are the kinds of queries, or maybe it says, is X an element of S? If it is an element of S, I want to delete it from S. Okay. So these are the kinds of primitives that this data structure supports. But now the other thing we are told is that this set S is a subset of some large set U. Okay, so it could be that there's this very large set U, which let's say is the set of all URLs. Okay, so there's a massive set. It's a very, very large set. But now, out of the set of all possible URLs, there's only a small subset that you're ever interested in. Okay, so now you build up a little table containing all which can store the subset that you're actually interested in. Okay, so this is called your hash table. And maybe the hash table has enough entries to keep track of n items. So the number of URLs you're interested in, the number of possible URLs, that's some very large number. So this has cardinality capital N, which is much, much larger than little n, which is the amount of memory you're willing to use. But on the other hand, you know that the number of, the size of S that you're interested in is much smaller than capital N. So that's why you're willing to use this smaller hash table. Okay, now what you do when you use a hash function is you pick some function h, which is your hash function, and if this is the URL that you are interested in, then you would actually map it under H. So if this was X, you'd actually put it in you would note in entry, you'd put X in location H of X. So H of X tells you which of these, where to place this item X. So this is where you'd go looking for it. Now, what happens if you have a collision? Suppose you have some other Y. And suppose that H of Y equal to H of X. Now you have a problem, right? So you've got to do something about it. And this is what you do in a hash table. You either chain or you rehash. Today we are going to talk about something very elementary. Okay, so you can do this analysis in many different ways. We'll do the most elementary analysis. We'll say, suppose we have no protection against collisions. Now, how big of a set can we store? Okay, so before we do that, we have to model this hash function somehow. So what this hash function is supposed to do is it's supposed to scramble up the bits of X and Y in some particular way, in some way, so that basically the hash function is supposed to behave randomly, right? It's like a random function. It takes X and puts it into a random location. It takes Y and puts it into a random location. Okay. So now you see where this comes up. It's a hash table. The entries of the hash table are the n bins. Okay. The items that we hash in. Okay. So we are assuming the cardinality of S is K. These are the balls that we are placing in the bin. The hash table, the hash function is this random function which is allocating each ball to a random bin. Okay? So therefore, this process of hashing is just like placing balls in bins. And so the question we are asking today is, suppose we created this hash table with no protection at all. So we did not apply any chaining rule. So if we got so suppose we did the most elementary thing where if we get a collision, that's it. That's a disaster for us. Right? We have to drop one item or the other. Okay? In this case, how big a set can we actually store? Okay? And the answer is going to be, well, how big can S be before we start getting collisions? And the answer is square root of n. Okay? Now, of course, there's a second thing we could do. We could say, well, but suppose that seems pretty harsh, right? I mean, that's a big penalty to pay. Now, suppose instead that we are willing to actually either do chaining or rehashing. Well, now the amount of time it takes to do a query, to do an elementary operation for hashing, is proportional to the number of collisions. So the actual occupancy of each entry, right? So the maximum occupancy is going to bound the running time. And so part B says, suppose that I really want to store a set which is as big as the size of the hash table. So if my hash table has size n, I want to store a set of cardinality n. Now how many collisions do I expect? And the answer is, well, it's still not too many. It's only log n. Right? Log to the base e of n. So if you want to sort of understand how big is, right, if you have log n versus 2 to the n, each of these is an exponential, right? One relative to the other. Right? So for example, e to the 8 is about 1,000. So log to the base e of 1,000 is about 8. E to the 10 is about 22k. And e to the 14 is about 1 million. Right? So if this is n, if this value was equal to n, then this value is log to the base e of n. Right? So the log function grows extremely slowly with n. And so this is saying that the number of items you expect, if you're storing if your set is of size cardinality n, and you're using a hash table of cardinality n as well, it's not going to be too bad, right? You get only so many collisions, as long as your hash function really behaves randomly. Now, okay, so how do you get your hash function to behave randomly? Well, that's another story which we may or may not get to, depending upon, how much time we have in this class. Okay, so is everyone clear about what we are trying to show? And why we are trying to show it? Okay, so now let's let's try to go ahead and analyze what's the so what we want to do is we want to say what's the probability that if we throw k balls in n bins, that all the balls land in different bins, right? Okay, so So in order for them to land in different bins, how many ways can they land in different bins? Okay, is that something that we can compute? It's not too hard, right? Because the first ball, it can land in any bin that it wants to. But now, whichever one it landed in, the second one had better avoid that one. So it's n minus 1. And then the third ball, well, it had better not land in these two bins. So it has n minus 2 choices, so on up to n minus k plus 1. Okay. These are the number of ways of placing the k balls so that they all land in different bins. But the total number of ways of placing the balls is n to the k. Right? So this is the probability that all the k balls land in different bins. Now, what's the question that we actually want to solve? We are not interested in computing this probability. What we are interested in is the inverse problem. What we want to know is, having computed this probability, we want to know what's the largest value of k so that this number is still greater than or equal to half. Right? We want to know what's the largest k such that this number is greater than or equal to 1 over 2. Right? Okay, that's what we were interested in. Or, well, maybe we don't want the largest. We want some large value of k. We want to know approximately how large can we choose k to be so that this number is still greater than or equal to half. Okay? Now, if you are suitably clever and good at working with numbers, you can eventually find your way to, figuring out what this k should be. And in the notes, you see this worked out in excruciating detail. Okay, but then it turns out that there's a simple way of getting a rough bound, and somehow, for our purposes, getting a bound is more valuable than getting the right bound. Okay, because we want to understand what's the correct order of magnitude. And it turns out that this rough bound we'll get is actually pretty good. It's really remarkably accurate given how rough it is. Okay, so we are not going to work very hard. Okay, and we'll end up getting a bound which is pretty good. Okay, so that's what we want to do next. So instead of using this exact expression, which we can write down and then we can sort of try to simplify it, what we'll write is an approximate expression. Okay? And so to write down this approximate expression, what we're going to use is a very useful bound called the union bound. Okay, so what's the union bound? What it says is, suppose you have an event A and an event B, then the probability of A union B is at most the probability of A plus the probability of B. Okay, what's the sentiment it's expressing? This is your sample space, omega. That's A. That's B. And if you're interested in A union B, well, the worst it could be is that A is sitting here, B is sitting here. They're disjoint, so you have to add up the probabilities. Of course, in general, maybe they intersect, and you are supposed to, the union is actually less probable than the sum. But this is at least an upper bound. Or we can definitely say that this probability is bounded by the sum. Now we can generalize this by induction, and we can say, well, the probability of A1 union A2 union so on A sub n is at most probability of A1 plus probability of A2 plus probability of A sub n. Okay? So that's the union bound. It says if you have a union of many events, you can bound the probability by the sum of the probabilities of the individual events. So now, let me show you two different scenarios, okay, in which, and you can tell me where it's a good idea to use the union bound. So here's one scenario. So scenario number one. Here's A1, A2, A3, A4, ... A7. Okay, so that's one scenario. And the second scenario looks like this. This is A1, A2, A3, ... A7. Okay? So now, in which scenario would you want to be using the union bound, and where would you not want to use the union bound? Yeah. The second one is where you want to use the union bound, right? Because when you look at the union, almost all the area is private to each of the events, right? So you're not losing very much by saying, look, there's these little places which I should really be subtracting off if I really want the correct bound. But it's so complicated, and, do we really care because these, the intersection is so tiny? I'll get most, the bound is going to be pretty good if I just add up these separately because the intersections are tiny. Okay? Whereas in this case, the intersection is almost everything, right? So if you add up the probabilities, you're going to get a gross overestimate. So in this case, the union bound is going to be terrible, whereas here it's going to be pretty good. Okay? So what we're going to do in that scenario we have up there is we're going to say, actually the union bound is really good, meaning somehow the events happen to look like this. Okay? Okay, so how do we do that? Okay, so we let A be the event, all k balls in different bins. Did I really want it to be like that? Okay, well, let B be the event A bar, right? Is that the notation we use? No? The complement of A? Yeah? No? Yeah? Okay. All right, so B is the event that at least two balls are in the same bin. Okay? So we want to show that probability of A is at least a half. So we want to show probability of B is at most 1/2. So we want to pick a k, the largest k, so that the probability of B is at most 1/2. And now what we say to ourselves is, well, how does B happen? Right? For B to happen, there must be two balls that ended up in the same bin. Okay? So we have balls numbered 1 through k. So maybe there was ball number I and ball number j. What's the probability that they end up in the same bin? What's the probability that I and j end up in the same bin? Well, here's how you can think about it. Go ahead and place I wherever it goes. It's placed in some random bin. And now what you want is, conditional on it being placed there, you want j also to go in there. Right? So the probability is 1/n. So B sub ij is the event that I and j in same bin. Probability of Bij is equal to 1/n. What can we say about B in terms of Bij? B is the union over Ij of Vij. Right? If B just says at least two balls in the same bin, in some bin, right? We pick all possible choices of two balls and then ask, and look at the event that these two end up in the same bin. So for B to occur, at least one of these events must occur, meaning B is the union of all these events. Right? So now what do we know from the union bound? The probability of B is at most the sum over all ij of the probability of Bij. Right? That's what we know from the union bound. If an event is the union of other events, then the probability of this event is at most the sum of these probabilities. Okay. So how many ij pairs are there? K choose 2. And what's the probability of Bij? It's 1/n. K choose 2 is at most k squared over 2 times 1/n. And we want to pick, we want this to be less than or equal to 1/2. So this is what we want. Right? We want that this probability of B should be bounded by 1/2, so that the probability of A is at least 1/2. So what should the value of k be? So if we want this to be true, we can guarantee this by picking k equal to square root of n. Right? Okay, so what happened here? So what we started with was we had an event A. We wanted to compute we computed its probability, and then we didn't like the expression that it gave us because we weren't really interested in the probability of A. We were interested in what value of k should we choose so that the probability of A is at least 1/2. What's the biggest value of k we can choose which still guarantees that probability of A is at least 1/2? And that looked like that looked like a question we could solve, but it was unnecessarily complicated. Right? And so instead, what we did was we used an approximation, and the approximation is of this kind, where we sort of thought to ourselves, these Bij's they look like this. If you look at the Bij's, if you go back and think about it in your free time, and you say, well, what do these Bij's look like? What you'll notice is that the intersections are extremely tiny. Okay? And so if you want to estimate the probability of the union of the Bij's, which is what we want to do here, then we don't lose much at all just by taking the sum of the probabilities of the Bij's. And this is something that works over and over and over again. And so it's a very good strategy. Okay, so in this case, we actually happen to have a closed form solution for the probability of A. In many of the things, many cases that we use the union bound, we don't even have a closed form solution. We don't even know how to write down the probability. But on the other hand, we can approximate it very easily. And we get an upper bound, and that's all we are interested in. So this is a technique which is extremely useful, in many, many, many situations. It takes complicated problems and turns them into simple, analyzable problems where we get very good bounds. Okay, so this told us that if we want to do our hashing in this way, completely unprotected, where we, as soon as there's a collision, we just drop the ball. Then we can, then the largest size set we can really make use of is square root n. How many of you have heard of the birthday paradox? Yeah? Okay, so let me just review it very quickly, and then we'll see. By the way, how many of you see that we've been talking about the birthday paradox? Okay, so let's talk about this for a few minutes, okay? So the birthday paradox is this. You're in a class of a reasonable size. Okay, this is not a class of a reasonable size. Okay, you're in a class of a reasonable size, like 30. Okay? And then you want to know, could it be that should you expect two people in that class to have the same birthday at random? What does your intuition say about it, if you've never heard about the birthday paradox? Right? There are 365 days in the year. What should the chance be if there are 30 students in class? Right, so you might think the probability that two have the same birthday is 30 over 365, which is very small, 1 in 10, 1 in less than 10, 12. Okay? Actually, by the time you have 30 students, your chance of two people with the same birthday is quite large. It might be 90%. Right? It's already 50% when you have 23 students. And by the time you have 60 students, it's over 99%. Okay? So, does anyone see why this is the same problem that we've been talking about there? Can anyone say in what way this is the same problem? Yeah. Okay, so this corresponds to balls, this corresponds to bins. Very good. Right? So if you think of the birthdays as being each student as having a random birthday, right? Then, and you have 30 students, well, if you want to know, so you have 365 bins, those are the possible birthdays, and then you distribute the 30 students randomly in those 365 bins. You want to know, is there a collision? Do two of them fall in the same bin? So now we want to know, how many students what's the largest number of students we can have, right? Such that the chance of two of them having the same birthday is still less than a half. Right? It's square root of 365, right? Which is about 20. Right? So this bound that we got, which was very we did this approximation here, which looks totally insane. Actually, the bound is really good. So this approximation was pretty good, right? And the answer is, you should start expecting, when you have a set of when your birthdays, when the number of days of the year, if the number of days of the year is n, and you have, by the time you have square root n students, you should expect to see two who have the same birthday. Okay, so any questions? Okay, so should we take a minute break before we move on to... So we are doing one more case today, which is what happens when we have n balls in n bins, right? And that corresponds to load balancing, and also this when we can allow for collisions in the hash table. Okay. But let's take a 1 minute break before we do that. Okay. Okay. So now let's talk about this this problem when we are going to do a particular case here, which is when there are exactly n balls and n bins. But the fact that we are doing this case is just an accident. You can repeat this analysis for m balls, n bins, and you can change the numbers. It's all very robust, but just for definiteness, we are just going to let these two numbers be the same. Okay, so the reason to consider this case is there are two reasons. Okay, one is where our set is of cardinality n now, and we want to know how many collisions should we expect. What's the maximum number of collisions we should expect? Okay. The second reason we want to do this is to analyze load balancing. Okay, so the motivation here is now these n bins are n processors in a distributed computing environment. And we have a number of jobs that come in. And we want to, the jobs are the balls, right? And we want to allocate these jobs to processors. Now, of course, the way we want to allocate them is, we want to distribute them out uniformly. One way you could allocate these jobs uniformly is, of course, you go down one by one and you keep allocating them. Okay? But that requires centralized processing or a lot of communication between processors. Okay? But also, in this case, the other thing that happens here, once you look at the full scenario, is that jobs arrive, and processors, this keeps going on. This is a dynamic situation. So n here is roughly the number of jobs that are alive at any given time. So the processors complete jobs, and so they may have several jobs stacked up, and some of them keep getting completed. And as they get completed, you can start allocating more jobs to them. And so, how should you do this? So one way of doing this, which requires no coordination at all, is to just assign each job to a random processor. And now if you assign each job to a random processor, what we want to know is how far from uniformly balanced is the load? Right? So if there were exactly n jobs and n processors, the best you could have done was just assign everybody one job, every processor one job. Now what we want to know is how much worse are we doing by the fact that we did not spend any time coordinating, but as each job arrived, we just threw it to a random processor. And the answer is log n over log n. Right? This is the maximum load with high probability. Okay, so that's the problem that we want to analyze. Okay, so how do we analyze it? Okay, so this time, it's very hard to write down a closed form solution. So this time we really have to lean on this union bound very heavily. So what do? We say, okay, so let's find the value of j. Let's find now what we want to do is find smallest j. Okay, so we want to say the worst that can happen to us is one of these bins is going to have j balls. Right? So we want to say maximum number of balls per bin is j with probability at least a half. Okay? So we want to figure out what's this value j. Okay? All right, so let A sub j be the event that some bin has at least j balls. So what we want to show is probability A sub j is at most a half. Okay, so that's what we want to do, and then we'll be able to say, well, actually it's clear that no bin is going to have more than j balls, with probability at least a half. Okay, A sub j is a very hard event to analyze. Okay, because now what we are saying is we've placed these n balls in these n bins, and one of those bins has at least j balls. It's, once it has at least j balls, how many does it have? We don't know. And what does it do conditionally to the other bins? This is all very difficult to analyze. Okay? So instead of doing that, what we are going to analyze is a much simpler event. The simpler event is bin number 1 has at least j balls. This is a much, much simpler event to analyze. So let's call this A sub j1. Okay? What's the probability of A sub j? 1. Okay, well, I don't know, but suppose we could make sure. Okay, so suppose we can make sure that probability of A sub j1 is at most 1 over 2n. Okay, so suppose choose j such that this condition holds. Okay, so suppose we pick j so that aj1 is at most 1 over 2n. Now I claim that we are done by the union bound. Okay? Why? Because A sub j is the event that one of the n bins has at least j balls. So A sub j is A sub j 1 union A sub j 2 union A sub j n. Remember, the thing in the parentheses says which bin number. Right? A sub j says some bin has at least j balls. This says the first bin has at least j balls. That says the second bin has at least j balls. So this is saying if some bin has at least j balls, the only way that can happen is if either the first bin has at least j balls, or the second one does, or the nth one does. Okay? But now, by the union bound, the probability of A sub j is at most the sum over some of these probabilities, probability of aj1, probability of aj2, and so on. The sum of these, right? The sum over I of probability A sub j I equal to 1 to n. But what's the probability of AJI? What's the probability that the ith bin has at least j balls? Well, it doesn't matter what I is, right? It's just one of the bins. All the bins are identical, right? They look the same as any other. So these probabilities are the same for every I, right? So this is just n times the probability of aj1. But if we showed that the probability of aj1 is at most 1 over 2n, this would be n times 1 over 2n, which is a half, as we wanted. Right? So we wanted to show that probability of aj is at most a half. And what we showed is, if we could show that the probability of aj1 is at most 1 over 2n, we are going to be done. Okay? Because of the union bound. Okay? So now let's figure out how to show that the probability of that the first bin gets at most j balls, at least j balls, is going to be at most 1 over 2n. For some choice of j. What choice of j? It's going to be log n over log n. Okay? So if we choose j equal to log n over log n, we are going to show that this holds. Once we show this holds, then we say, well, how can, what's the event we're actually interested in? We are interested in the event that some bin has at least j balls. But then there are only n bins, so the chances, by the union bound, it's n times what it is for the first bin. So you get n times 1 over 2n, which is a half. Okay? Okay, so again, the main point of doing this is showing you why the union bound is so relaxing to have it. Right? Because these are complicated questions. If you really wanted to write down the probability, this would be a very hard question. We don't have to write down the probability because we can simplify the question. We can just say, just estimate it like this. Okay, so now let's do the last step. How do we figure out, how do we compute what's the probability that the bin 1 has at least j balls? Okay. So here's bin 1. We want to know, and here are the balls we want. Let's say we have j equal to 3. So we want to know what's the probability that at least 3 of these balls end up in bin 1. So maybe it's this one, this one, this one. Maybe all these end up in. This is one way it could happen, right? Maybe all these end up there, and maybe some of these do too. But I could pick this subset and insist that these 3 should end up in here. So suppose j equal to 3, right? If I pick this subset S, and I insist these 3 end up here, and then I don't care what happens to the rest, right? I know that the event has happened. AJ1 did happen because these 3 balls ended up in bin 1. Okay? So now I can say, let B sub S be the event that this subset S, subset of of the n balls of cardinality j, right? These S ends up in bin 1. Okay. B sub S is the event that I picked out this set S of these j balls, and I insisted that all of them end up in bin 1. Okay? So now, what I claim is, if j balls end up in bin 1, the only way that can happen is if for at least one of these subsets S of cardinality j, B sub S happens. Right? It's got to be the case, right? Because at least j balls ended up in bin 1. How could that be? Well, there must be some subset S which I can point to and say, these balls all ended up in bin 1. So I can say A sub j1, this event, is equal to the union over all S of cardinality k of B sub S. Right? Okay, but what's the probability of B sub S? So once I pick these balls, what's the probability that they'll end up in bin 1? Well, there were j of them, right? Each of them has got to end up in bin 1. What's the probability that it ends up in bin 1? 1 over n each, 1 over n to the j. What about the rest of the balls? Well, I don't care where they end up, so they don't affect the probability, right? They can end up anywhere they want. That's probability 1. Okay. So now, what if we apply the union bound? So probability aj1 is at most sum over all S such that cardinality of S equal to k of the probability of B sub S. Well, all these B sub S's have the same probability. This is 1 over n to the j. And how many such subsets are there? So, sorry, S equal to j, right? How many such subsets are there? There were n, out of n elements, we are picking j. N choose j. Right? Out of n things, we are picking a subset of j of them, so there's n choose j, which is equal to n into n minus 1 into so on into n minus j plus 1 over j factorial 1 over n to the j. Right? Which is at most, this is n to the j divided by j factorial n to the j. So that cancels. So it's at most 1 over j factorial. Right? So we said probability of aj1 is at most 1 over n to the j, 1 over j factorial. So that's what we've ended up with. Probability aj1 is at most 1 over j factorial. Okay. Now we want to know how should we choose j so that, remember what our goal was. We wanted to pick j so that this probability was less than or equal to 1 over 2n. Right? So we want to pick j such that 1 over j factorial is about 1 over 2n. Right? What's j factorial? J factorial by Stirling's approximation is about j divided by e whole to the power of j. right? So now, so what we want is j divided by e whole to the power of j is about 2n. So we take logs of both sides. We get j times log j, ln j, minus 1, right? Log of e is 1. Oh, sorry, I'm doing this too fast for people. So take logs of both sides, right? When you take logs, the exponent comes down, so you get j times ln j divided by e is about ln 2n. Okay, ln 2n is, so this gives us j times ln j minus 1 is about ln n plus ln 2. This is a constant. Okay, I'm going to throw away these constants because between friends, who cares? Right? And so now we have j ln j is about ln n. Okay. Okay, so now you already, if you throw away this ln j, you get j about log n. And if you keep it around, then this solves to j about log n divided by log n. So this log j, sort of when you pull it down here, so without this log j, you get j about log n. And so when you throw back in this log j, so if j is log n, then log j is log n. So you should, when you pull this over to this side, you should divide by log n. Right? So that's where this comes from, roughly. Okay, so I'm doing these calculations very roughly, but that's just to show you where this bound came from. Okay?